Welcome back to Calculus 2, Section 7.3, Polar Coordinates. Let's begin by looking at the definition of polar coordinates. Here we're looking at the x, y coordinate plane. We have a 0 to indicate the origin. And then let's think about if we wanted to plot a point in the xy plane. We would go and we would look on the x-axis for a value x. Likewise, we'd look on the y-axis for a value y. We would think about a vertical line going through this point on the x-axis, a horizontal line going through this point on the x-axis, and then where those two lines intersect would determine a point. That point would have coordinates, first x and then y, x comma y. That is defining a point which we can term P, and its position is given by the coordinates x and then y, and this is done in the Cartesian coordinate plane. What we want to do now is come up with an alternate system and look at this same picture, but in the lens of polar coordinates. And then the way that we'll go about doing that is by considering right triangles. What we've done is we have taken the point P, drawn a line segment to the origin, and then from there create a base and a second side, a height. Note that the two sides create a 90-degree angle. This is a right triangle. The measurements of this right triangle, well, the sides will measure x and y. For convenience, we've started out by picking a point P in the first quadrant. Nicely, that makes both the x and the y positive quantities. Had we instead picked P to be, for example, in the second quadrant, the y-coordinate would remain positive, but the x-coordinate would be negative. Likewise, in the third quadrant, a point P would determine a negative x quantity. So think of these as measurements, but really they are technically just labels, as they may be negative valued. Okay, now for the hypotenuse, we're going to introduce the variable r. Think of that as radius. But that's the hypotenuse of a right triangle, and for a right triangle, we have the Pythagorean theorem. You want to be very comfortable with the notion that this equation, x squared plus y squared equals r squared, determines all points P that lie on a circle of radius r centered at the origin. That this P is only one particular point in the set of all points exactly r away from the origin. And this P corresponds with a certain angle with the x positive axis, and that's basically the notion of polar coordinates. So, to affect that, let's bring in the acute angle theta here in this right triangle, and then think back to elementary definitions for trig functions sine and cosine. On cosine of this acute angle, you would look at the adjacent side and quotient that with a hypotenuse and produce cosine of theta. For sine of theta, you look at the side opposite on the right triangle and quotient that with the hypotenuse to get the value for sine of theta. Allowing, again, x's and y's to be negative would then produce either positive or negative values on sine and cosine, but is also going to help us identify points in their correct quadrants. Nice. Now, as we are trying to cook up a new coordinate system, And the new coordinate system will have variables r and theta. Our coordinate system we understand has variables x's and y's. Looking at these definitions for sine and cosine, we have a mixture of rectangular x and polar r. We're going to rectify that simply by multiplying both sides by r. And then we can see that we have a nice situation of Cartesian coordinate x on the left, and then on the right-hand side, polar coordinate r, and polar coordinate theta on the right. And then that is also the situation, Cartesian on the left and polar on the right. So these are very important. And we take these two as a pair, and then we're going to add one more equation to this Pythagorean theorem statement as a way to produce thetas. So looking at the right triangle, and if we want to involve x and y, we can use y over x. That would be the opposite side over the adjacent side, and then call that tangent. Tangent of this angle. And so that's what we'll do. And then these equations will help us go and transform from one system into another. If we want to go from polar to Cartesian, these are the equations that we'll use. Come back up here. Introduce the tan of theta, y over x, tan of theta. And this is what we'll use if we want to convert from Cartesian to polar. And that's exactly what we'll do next, is we'll look at converting between the coordinate systems. So here's where we were. And note that there are two scenarios. There's the scenario of going from Cartesian x's and y's to produce an r, x's and y's to produce a theta. And there's the scenario of going from polar to produce Cartesian, r's and theta produce an x, r's and theta produce a y. Let's do some examples. Convert the coordinate x comma y taken as 1 comma 1 into polar coordinates. Well, we want to go from x's and y's and produce r's and thetas. So we want to go from Cartesian to polar. We have a value for x, 1, a value for y, 1. So 1 squared plus 1 squared is going to give us 2. So r squared will be 2. Write that down. We get that r squared is 2. Applying the radical, we get that r is rad 2. Plug in for the tan theta equals y over x. That's 1 over 1. Tan theta is 1. Now you have to pause for a second and consider the location in the plane of this point. Since both x's and y's are, the x and the y are positive, we are in quadrant 1. And then in quadrant 1, an angle, which is terminal in quadrant 1, is pi over 4. Tan of pi over 4 equals 1. Nice. So in rectangular coordinates, the first coordinate is x, the second is y. In polar coordinates, the first coordinate is r, and then the second coordinate is theta. So it's r theta, r theta. Thus, rectangular 1 comma 1 in polar coordinates is rad 2 comma pi over 4, r theta. Here are some more for you to play around with. Don't be thrown off with this negative pi. Negative pi is just a number that is taken as the radius. Nice. Okay, so we've done examples of going from rectangular to polar. Let's go the other direction. Polar r thetas into rectangular x's and y's. Note we have an r value of 1, a theta value of 3 pi over 2, and the instruction is to go from polar to Cartesian. So we have r's and thetas, and we want to produce an x. We have r's and thetas, we also want to produce a y. We know that r is 1 and theta is 3 pi over 2. Plug that information in. Cosine 3 pi over 2 is 0. Sine 3 pi over 2 is -1. And so we produce in rectangular coordinates, the polar coordinate 1 comma 3 pi over 2 is the same as 0 comma -1. Excellent. And then here are some for you to play around with, the r and then the theta as specified. Excellent. Finally, let's think about graphing functions in a polar plane. When we graph a function, we could label the graph y equals f of x. That's standard, y equals f of x. Here, in graphing functions, we're going to see that the r will be the dependent and theta will be the independent. To get into graphing functions, however, let's think about how to graph points. And then in this picture, we're looking at coordinate axis for x and y. And then there is the origin here. Let's begin with the origin. So the origin of the Cartesian plane is called the pole in the polar plane. So we're going to refer to the origin as the pole. Think of it like the North Pole. If you could go to the top of the world from space and look down, and then think about a pole at the top, that would be the axis that the Earth would rotate about that axis. All right. In both Cartesian and polar coordinates, the pole, the origin, is given by coordinates 0, 0. R equals 0, theta equals 0. Determines the pole. Next, we want to know this vocabulary. The polar axis originates at the pole and then follows the x-axis in the positive direction. That is the polar axis. And that's what we want to reference when making angles theta. Now, let's note that we have 3 concentric circles plotted here. I've highlighted one of them, the innermost, in pink. And then let's suppose that the distance of any point on this pink circle to the pole, let's suppose that it's 2. Then we can simply specify that we want a radius of 2, and then that equation, r equal 2, completely defines this circle centered at the pole of radius 2. Note that when we mark on the polar plane, that we can put positive 2 on each of these axes, as that is specifying how far this point is to the pole, that these are all positive 2, as in indicating an r value. Likewise, let's look at the other 2 circles, and let's suppose that they correspond with r equal 4 and r equal 6. Nice. Okay, let's come back and look at that polar axis, and now let's consider thetas. We've considered r's. R's specify the distance to the pole. Thetas, what do thetas do? Thetas indicate an angle formed with the polar axis. So here's one drawn so that it might correspond with pi over 3. Take a look at the pole. If we move from the pole and we follow the direction of this ray, which forms an angle of pi over 3, if we move in that direction, in the positive direction, let's say 2 from the pole, then what we've done is we have specified a point in the polar plane where r is 2 and theta is pi over 3. And then I put a little arrow here to indicate that we're opening up a positive angle, the counterclockwise direction. Nice. Alternatively, open up a positive angle theta, 4 pi over 3. Put yourself back at the pole, but instead of following the direction of 4 pi over 3, go in the exact opposite direction of 4 pi over 3 and go a distance of 2, but in the opposite direction. To indicate opposite direction, let's specify r radius as -2. R as -2. And then that would produce the same point that we had earlier, but then we note that it's a curious behavior. If we have any angle theta, and if we add pi, then we simply put a negative on the r, and we have the same point again. If we have theta and add 2 pi, then we keep the r. So there, in fact, are an infinite number of ways to describe a point in the polar plane, something that is different with the Cartesian plane. Nice. So here are some points for you to describe in the polar plane. And for each point, please pick a positive r value and a negative r value to describe the 3 points. Okay. I mentioned earlier that when graphing in a plane that we would use y equal f of x, here we have r equals f of theta, where f is sine. And you want to think of the theta as the independent variable and the r as the dependent variable. That r values are produced by inputting theta values. So to go about plotting a curve, let's begin by plotting points. To plot points, we want to specify first the independent variable, theta, and then produce a dependent value, r. Okay, so start with theta being 0. You get r is 0, which is the pole. That's easy to plot. Try another one. Try theta, independent theta, being pi over 6. Then r of theta, that sine of pi over 6, is 1/2. So you want a circle of radius 1/2, and then on that circle, pick the one that corresponds with theta being pi over 6. Now increase from pi over 6 to pi over 4. Find that r, the radius, will be rad 2 over 2. Increase again to pi over 3. Theta is now pi over 3. R would be rad 3 over 2. Plot that point. You're moving further and further away from the origin. You'll move the furthest away from the origin when theta is pi over 2. That's going to be a distance from the origin of 1. These are sample points done for acute angles between 0 and pi over 2. If we think of obtuse angles between pi over 2 and pi, this function sine will be positive, and we can, by symmetry, simply reflect these points into quadrant 2. Doing so, we can then connect the dots. They will connect in this nice circle. Note that to traverse this circle, we use 0, pi over 6, pi over 4, pi over 3, pi over 2, and then we came back when theta was pi. So 0 to pi for this parameter theta traverses this curve. Note that the diameter of this circle is 1, therefore the radius is 1/2. So this circle, which is lying about the y positive axis, is centered for a y value of positive 1/2. Nice. Repeat the previous exercise, but instead of positive sine theta, use negative cosine theta. You should find that you get the same picture, but with the center at x equaling negative 1/2. Beautiful. Okay. We are looking at our previous example. We have the curve, the polar curve, sketched. Let's try and get comfortable with going back and forth. We have a polar equation, r equals sine theta. Let's turn that into a rectangular equation. So what can we do? Well, r, we're pretty familiar with r. Sine theta, you want to recognize, oh, that was given in the equation to produce y's given r's and thetas. But we are missing an r. So give the right-hand side an r. But you have to be fair. If you give the right, then you also must give the left. Nice. Aha. I can simply now swap in both sides my conversion equations. R squared is the same thing as the sum x squared and y squared. R sine theta is the same thing as y. Voila. R's and thetas have now turned into X's and Y's, and you do algebra. Good. New techniques now. We're doing simple algebra. Let's first move the Y to the other side. And then we'll complete the square in Y's to get that this difference of a quadratic and linear term can be written down as a binomial squared. That will require having the coefficient on the linear term and then squaring that to get 1/4 and adding 1/4 to both sides, and then rearranging the left-hand side. The nice thing is that 1/2 times 1/2 gives a quarter, meaning that the radius is 1/2. And then we look, this is the same thing as x minus 0. So 0, positive 1/2 is the center of the circle described by this equation, which we already have plotted. Nice. So we see that this polar curve r equals sine theta is equivalently defined by this rectangular equation. Beautiful. You try the same thing. Here's a polar equation. Go about in the same manner, converting it to a rectangular equation. Notice what it is to be able to plot it in the plane, and then recognize that that curve can either be plotted by the rectangular equation that you produce or this polar equation. Note, you can simply go into Desmos and type this verbatim, and Desmos will produce the curve for you. Excellent. We are plotting curves, and in doing so, we noted that the r is the dependent and the theta is the independent variable. So here, this equation is saying, oh, I would like to take the independent variable to be some fixed value. All right, so what does that do? Well, we can look at the tangent of both sides, come up with tan theta equaling some value, here in this case, negative rad 3. And then that's our ticket to be able to convert from a polar equation into a rectangular equation because we have an expression. Tan theta is y over x. Very nice. Since multiplying both sides by x, we can come up with a familiar type of equation. This is a line that goes through the origin with this slope, negative rad 3. Boom, we can nicely plot that. And thus, this blue curve is the graph of this polar equation, theta equaling 2 pi over 3. Think about the angle 2 pi over 3, that's an obtuse angle. So if r's are positive, then you're picking a point in quadrant 3 on this curve. If r's are negative, then you're picking a point in quadrant 4 on this curve. Fantastic. That's it. All right. So polar curves, a particular type of polar curve is called a limacon. A limacon comes in 2 different flavors. A is a constant, like 1 or 2 or 5 or negative 7. B is likewise a constant. Cosine you recognize as the trig function. Theta, you know, is the independent polar variable. R is the dependent polar variable. Limacons come in 2 different flavors. One specified by cosine, and the other where you specify it using sine. And then the different varieties of limacons depends on the quotient of A's and B's. Let's watch a video. All right, so here is plotted out, thanks to Desmos, a nice instance of a limacon using sine. Then I'm going to play the video, and as we watch, this limacon will change its shape. Currently, the bulk of the limacon is occurring in the lower half plane, and it will deform and eventually result in part of it in the upper half plane. Note nice symmetry about the y-axis, and that's because this limacon is given by sine. Let's watch this deformation. Now in the upper half plane, And this is simply by changing the values of A and B. Okay. So to investigate that, try now yourself instead of sine using cosine. You should find that when using cosine, that you will have symmetry about the, not y, but the x-axis in your assignment here. And as you do so, the one that will play a big role is when the a and the b quotient to plus or minus 1. And that instance of a limacon is called a cardioid. And the reason why it's called a cardioid is it kind of looks like a heart. Note, as I mentioned, that in this instance of the limacon, given by a cosine term, that we have symmetry about the x-axis. And when the a and the b are in quotient plus or minus 1, then you get a picture that looks like this or that looks like this. Nice. And all that's done is, since a and b are the same, swapped out b for a and then factored off the a. Okay, so cardioid is a particular limacon. Excellent. So give this a shot, plug it in, plot this cardioid, and that finishes this video. Thank you so much for watching. I will see you on the next one.